Now case number 2, the root of the denominator f of s are real and repeated. So if I have the function which given to me in Laplace domain, its denominator is real and repeated. First of all, I need to know what's the meaning of repeated. Notice here that in the denominator of this function s plus p 1 to the power r, if it's to the power r means it's repeated. So when we try to find the equivalent of this function, the repeated is to be written as k1 over s plus p to the power r, then followed by k2 over s plus p1 to the power of r minus 1, and so on. And the non-repeated functions or non-repeated roots, they are going to be same as before. I mean, they are going to remain the same and we will treat them same as before. And the constants for the non-repeated quantities, non-repeated denominator, to be calculated same as in case 1. How about the repeated? For the repeated, we are having this equation, which we are going to use it to calculate those constants. Like for example, if I want to calculate K2 as shown here, let me just erase this. If I want to calculate K2 here, to calculate K2, its denominator is a repeated function. That's why we will calculate it using this formula. Keeping in your mind that to calculate K2, 2 is the second repetition of the function. That means I will be equal to 2. So in this case, I equal to 2. And equal to 1 over I means 2 minus 1 factorial into the differentiation. I mean, it's going to be I minus 1 differentiation of f1 of s over ds of I minus 1, where f1 of s is to be calculated as you can see here. So it's equal to the denominator of the repeated function multiplied into the function. Let us see the example in the next slide. Hopefully it will make us clearer. Here is example on real and repeated. In this example, you want to find the Laplace inverse of the function given here. So we are going to follow the procedure by finding the equivalent function to this one, similar to what explained in the method before in the previous slide. So you will, or the function 2 over s plus 1 into s plus 2 square have repeated function which s plus 2 square. So when we expand it, we are going to write it as k1 over s plus 2 square. This is the repeated function, which is not repeated yet. It's going to be repeated here, okay? Plus k2 over s plus 2 to the power of 2 minus 1, if you notice here, to the power of 1, plus k3 over s plus 1. k3 over s plus 1. So remember, s plus 2, I mean, let me just erase this. Remember that s plus 2 to the power 2 is expanded as s plus 2 to the power 2 in the first item, and s plus 2 to the power 1. When it's to the power 1, we finish the repeated function. Then we will go to the other part, which s plus 1. So it's going to be written as a k3 over s plus 1. As noticed here, or as I'm showing here, this is not repeated now. This is not repeated, and this is repeated. So for the non-repeated, it's to be calculated same as case 1. Okay? Now for the repeated, I mean for the non-repeated, we can calculate K1. K1 can be calculated, and it's equal to minus 2. And K3 can be calculated equal to 2. K2, which is the repeated element, it's to be calculated by using the formula, so the equation given. So we can write the equation, which given in the previous slide, 1 over 2 minus 1. Remember, it was I minus 1. Here I equal to 2. 2 because this is the first repetition and this is the second repetition. So here I equal to 2. So when I want to calculate for this function, I equal to 2. So it's 2 minus 1 factorial into the derivative, which derivative is 2 minus 1, means I minus 1. So it's the first derivative. For what? For f of 1. f1 of s. f1 of s. So we calculate it and solve it at s equal to minus 1. So here he's trying to calculate, or he's calculating here f1 of s, where f1 of s is equal to the denominator of the repeated element, I mean the denominator of k1, or the repeated function multiplied into the whole function. The repeated function multiplied into the whole function. So when we multiply it, of course, s plus 2 square will be cancelled with s plus 2 square. The remaining will be 2 over s plus 1. So f1 of s equal to 2 over s plus 1, which can be written as a 2 into s plus 1 to the power minus 1. Let's just take this s plus 1 up. Now we will find its derivative to satisfy this element. Let's see in the next slide. So here df1 by ds, when we calculate it, it's equal to minus 2 over s plus 1 square. So we will solve this value, or this item, at s equal to minus 2. We will find that it's equal to minus 2. Now we find the constants, the three constants. We can substitute them in the first equation, or in the equation written earlier. It's going to be written as a minus 1 over s plus 2 square, minus 2 over s plus 2, plus minus 2 over s plus 1. So now this one, we can find it easily in the table. We can find these items in the table. So minus 2 over s plus 2 square, which in Laplace, when I convert it to time domain, it's going to be get this value, and following this rule. Okay, and minus 2 over s plus 2, it's similar to what is explained earlier in case number 1. This is found here, and minus 2 over s plus 1 is given here. Let me just change the color. It's going to be this one. So that's how we express the function in time domain. That's how we convert the Laplace equivalent, or sorry, the Laplace domain to time domain, as you see here. Similar example given here for real and repeated. Notice that we are having the function is g of s equal to 1 over s into s plus 1 to the power 3 into s plus 2. So remember, or notice here, that s plus 1 is repeated function, which will be repeated 3 times when we expand it. So when I write the function, or when I expand the function, it's going to be written as k1 over s plus 1 to the power 3 plus k2 over s plus 1 to the power 2. Remember, it's here 3, here is 2, and finally here it's 1. So we finish this part, which coming from the repeated function, and we put the constants k1, k2, k3 for them, just to differentiate between the repeated and the non-repeated. Then after that, we will continue with the non-repeated element, which a1 over s plus a2 over s plus 2. So we notice here, or we will find here, that to calculate k1, it can be calculated directly, because k1 is denominator is available in the function. It's the source of repeated, but it by itself is not repeated, but it's the source of repeated function. So once it's available here, means we can calculate it same as case 1. A1 and A2 can be calculated with the same way. The repeated element is K2 and K3. These are the repeated elements, or the repeated constants, K2 and K3, which to be calculated using the formula I explained earlier. Here he calculates A1, here A2, and then K1. Now to calculate the repeated function, we are going to use this equation. We will calculate f1 by multiplying g of s into the repeated element. So f1 of s will be 1 over s to the power 3. Or 1 over s, sorry, into s to the power s plus 2. I mean, this is f1 of s, which we need to differentiate it as given in this equation. So in the next slide, here you need to keep something in your mind. I, what is I? What is the value of I? I, as I told you, if it's s plus 1 to the power 3, when I want to expand it, after this one, it's going to be s plus 1 to the power 2. After that, it's going to be s plus 1 to the power 1. So notice here that this function is repeated 3 times. Here we are assuming I equal to 1, here I equal to 2, here I equal to 3. So when I want to calculate for this part, which actually given here as K, I think it was K1, oh, sorry, A2, A2, when I want to calculate for A2, I equal to 2. When I want to calculate for A3, I will be considered equal to 3. And you can substitute I here in this equation. Let's see in the next slide. So here, if you notice, I, when he calculate K2, not A2, K2, when he calculate K2, I is equal to 2. So when he substitute I equal to 2, we will substitute in the equation and we will find that the derivative of the function here is expressed here. So when we substitute or when we solve it at s equal to minus 1, we will find that k2 equal to 0. Similarly for k3 consider I equal to 3. I equal to 3. So here we'll find the second derivative. And here it's 1 over I minus 1. So 3 minus 1 I over 2. But 2 factorial or 1 factorial is the same. And here we will find the second derivative of this function. We already find the first derivative here. So you need only to derive this one to get the second derivative after that. So here is the result of the second derivative for that function. When we solve it at s equal to minus 1, you will find that k3 equal to minus 1. We substitute the values in the main equation. We'll find that it's written as minus 1 over s plus 3 to the power 3 minus 1 over s plus 1 plus 1 over 2s plus 1 over 2s plus 2. Now we will solve them using the table given earlier. So the first one, 1 over s plus 1 to the power 3. Here is its solution or its time domain. And for this function, it's minus 1. Minus 1 is the constant and exponential of minus 2 and so on. Case number 3 is the root of the denominator of f of s is complex. So when it's complex, how am I going to deal with it? Complex, as you see here, if you have f of s, which we have in numerator and denominator, in the denominator we have complex function. Let's say this is complex. How am I going to deal with it? That's what we are going to check here. So to calculate K1, we will follow the same style as in case 1. And to calculate K2 and K3, we will balance the coefficient of the equation. And you will see how it's to be done in the example after a while. Let's look at this example. Find the Laplace inverse of the function given here. So f of s equal to 3 over s into s squared plus 2s plus 5. Make sure that this function is complex before you start. Make sure that the function is complex. You can use your calculator to confirm it. To confirm it very fast. So once you find it's complex, we are going to follow the style in this example to do it. So how to expand it? F of s can be written as equal to 3 over s into s squared plus 2s plus 5, which equal to k1 over s. K1 over s. Now we are having here two values for s, so it's to have two k's. So it's to be written always as k2s plus k3, always to be written like this, k2s plus k3 over the complex element. Now in the way of the solution, we will multiply the whole equation into the denominator of the function, which s into s squared plus 2s plus 5. So, and keeping in our mind that the value of k1 is to be calculated, as I mentioned earlier, as in case 1. So use the value of k1 in the equation. So when you multiply this value into the whole equation, at this side you will get 3. And when you multiply the whole quantity here into this side, s will be cancelled with s, the remaining will be this one. And when you multiply it into the third side or the third part of the equation, this bracket will be cancelled with the bracket there, and the remaining will be s, as you see here. So that's what we are going to get here. Now let us simplify the equation, rearrange it, and finally the equation can be written as you see here. We are just playing with it mathematically. We are going to get the equation as you see here. The equation is saying that s squared into bracket plus s into bracket is equal to 0. As you know, s squared and s cannot be 0. That means this part equal to 0 and this part equal to 0. If the two parts I mentioned earlier equal to 0, like this value equal to 0, from there we can calculate k2, which equal to minus 3 over 5, and we can calculate k3, which equal to minus 6 over 5. We substitute them in the equation earlier, and the equation going to look like this now. 3 over 5 all over s minus 3 over 5 into s over s squared plus 2s plus 5 plus 2 over s squared plus 2s plus 5. That's equation number 2. So these rules are needed for us from the table of Laplace inverse. They are needed whenever we have a complex function. If you notice, this rule is the cosine and the sine. Cosine will be needed when I have s over s squared plus omega squared. And sine needed when I have omega over s squared plus omega squared. So notice here a constant with here constant, here s with here s. If there is a phase shift, then this equation to be like this. S, of course, a is a constant. A is a constant always, it's no problem. It's going to be s plus a over s plus a squared plus omega squared. This is to be written as you see here. And here, the omega, if I have phase shift again, omega will remain here as omega. So always, guys, we need it. I mean, if I have this, then we can put it in a sine form. So always, whenever I come across such a function like this function, we need to put it in this format, in this one and this one. Okay, how this is going to be, let us see it in the next slide. Okay, here I'm showing, or I'm bringing equation number 2 to this slide to help us. If you notice, what are we going to deal with is whatever in between the bracket. I mean, between this bracket and this bracket. We need to rearrange them to put them similar to sine and the cosine function which available in the table. So to do so, let us check what he have done in the numerator. It was s. And in the denominator, it's something else. So I will start with the denominator. You will understand what I mean. When I look at the denominator, s squared plus 2s plus 5, we can write it as s squared plus 2s plus 1 plus 4 plus 1 plus 4. So if you take this part out of it, if you take this part out of it, this equation can be written as s plus 1 all square plus the 4 will be 2 square. So when you are doing it this way, this is actually what he put here. It's fine. Now we can look at the numerator again. I mean here and here. Now we can look at the numerator. If you notice here, we are having phase shift. Let me just erase this. It's not needed anymore. Okay. Now, when I have this phase shift, we need to show it here. Here it was S, as you see, it was S. So what am I going to do to make it similar to the denominator? We will add 1 to it. So I put it S plus 1. Of course, if I put plus 1, I have to subtract that one to balance the things. So it's going to look like this. S plus 1 over S minus 1 over S plus 1 square plus 2 square. Now, this one will be taken to the other side. So when I notice the denominator is the same. So minus 1 over this denominator plus 2 over this denominator, it will end up with 1 over s plus 1 square plus 2 square. That's very fine. Now I need to keep omega the same. This is 1 and this is 2. So I need to put 2 in the numerator. What am I going to do? I will put it half multiplied into 2. So half multiplied into 2, here I'm having omega and here I'm having omega. So the things are satisfied now. Now the equation is ready to be converted from the table. So here, if you notice, this part, it's a clear cosine and it's going to be replaced like this. And this part is a clear sine and is going to be replaced, as you see here, with half is the constant, will remain as it is. And the other part of the equation, you know how to do them. We have done something similar before. So that's the time domain of that function. He simplified it, and finally it's to be written as you see here. Okay, this is what is needed for us in Laplace transformation. We are very much caring about finding the Laplace inverse. I hope it's clear. In the next class, we are going to talk about the modeling of the system. We will start by electrical system. So in the next class, we will start the modeling of electrical system. I wish you all the best.